Hey folks, Dave McMillan here, lecturing on measuring tools, and these are hand measuring tools very specifically, and we're going to jump back and forth between slides and a live in-hand presentation a couple of times during the beginning of the lecture for those tools that I have on hand at home. Here we go. So the most fundamental tool is not quite the one you'll use the most often in a shop environment, but you will still use fairly often is a ruler or a steel tape. I'm going to do a demonstration about the subtleties of some of both. I'm going to start off with the tape because it actually has a lot of subtleties of design that are very elegant and helpful. I'm going to switch back to the live view here. The very normal tape measure comes in a compact hand-holdable fashion. The button on top is a lever lock, so it stays open, so you can do easy and ready comparisons. And just have out the appropriate amount of ruler. This one measures in nice, large, easy to read digits. It's in English or irrational units only. It has fractions of an inch on it. It's curved. And that lets it still roll up inside nicely, but it remains stiff and stays up. So it's a good design compromise. If you're measuring up a height, you can actually just take it and bend it and poke it up and get the height total by running it up against the roof. So it's a convenient way a lot of people don't know about for taking a height of a ceiling or another object that's out of reach. At the end here, a lot of people will say this little bit is loose. It's floppy. It slides back and forth. Yeah, so it's broken. You know, they gave me a bad one. Well, actually, this slides back and forth just the right amount that it measures correctly here when I'm placing this against the thing I want to measure the length of this way. And it measures correctly on this face when I press it against the thing I want to measure from. So this slides the exact width of that tab. Additionally, there's a little notch in there that's just the right size for a standard nail. So you can hook this around a nail and subscribe a circle, or take another measurement in a relative length of the nail. And I can't remember, I think it's a 3-penny nail or something. This ends up being dead zero on the center of the head of the nail. It's sort of a rafters or house frame builders trick, but can still work for a basic pivot. So that's about it for a hand tape measure. Very useful, particularly if you need to measure something that's 20 feet long. And a precision measure or a steel rule, or in my case a wooden ruler. This is my is it the Rulers of Science ruler. And this one has inch and centimeter co-scribed on it. If we jump back to the slides here, you'll see that the ruler here doesn't actually have zero set on the edge of the rule. And that's the manufacturers saying, we didn't make this to a level of precision and length that's meaningful. So start your measurement here, right? So this end is not square. And it's actually, it wears nicely. Like, so if you used it again and again and again, it would project the zero of that ruler. Where it wouldn't change. As you think one that went all the way to the edge, right? If it wore out a little, the whole rule would become inaccurate. This ruler here, let's see, not used to this reverse interaction. It does go to the zero, but this is a stamped piece of wood. I wouldn't hold it out. I have a nice Starrett rule at work that is square and runs up against the zero. Interestingly, it's a metric dominant rule, so the other end, which is 300 millimeters, ends there, and the inch is just dropped. The fractional inch is just dropped at the end. So some subtleties with rulers. Going back to the slides there, you'll see on the right there's a ruler with a little hook edge on it to make it more convenient. There's a ruler with a taper on it. This is just a straight edge, so if you need to know the straightness of something, it's a handy device. Most rulers can function as straight edges, but you're really presuming that they're straight. You don't actually know unless you bought a straight edge and the manufacturer of the straight edge says this edge is straight across its entire length within an N. and then you know that if it lays up flat against something, that it's that straight, or that the deviance is such amount. The tool you will use most likely, most often in a shop, is a dial caliper. This is technically a digital caliper because it shows a digit, as opposed to a just a length caliper, which you would read off. But let me switch back here. This is the more modern digital caliper, and you can see it actually reads a value. When the jaws close or open, that value changes, and it should run down to 0, close to 0. May need to recalibrate. All of these come with accuracy stated when you purchase it. This one is 8-inch, which I prefer. It fits the hand a little better, but 6-inch is more common. You can get them in 1 foot, 2 foot, 3 foot, 4 foot. Price goes up exponentially because they have to be made out of more and more complex materials. But this device can be used for reverse engineering anything. Essentially, with a piece of paper or CAD software in hand, I can begin to start taking measurements on this. So this is 0.9125 inches. I would measure it in a couple of places and see how round it is. So it's 2 thousandths difference, 3 thousandths difference. So it's not quite round, but that would let me set the tolerance if I wanted to describe that there. Another nice thing about the modern digital one is I just click a button and my measurements are now in millimeters. So I can work in either unit. So there's 5, let's see, 1, 2, 3, 4, let's say 4. I don't want to get into the subtleties of it. There's 4 major ways to use this caliper for measurement, right? So I can do as I demonstrated before, right? This is an outside measurement, right? I could have an inside measurement with these 2 jaws. And let's say I wanted to know that width of that hole. I can open it up there, and that's 0.122. So there's probably a metric hole in the die there. Then I can use this long tail here as a depth gauge down in a slot or a channel. So going on the side of the bottle here, I can take that measurement, and that's 0.1097. And then there's one more subtle one, which is hidden on the back. If you can see, when this is fully closed, the 2 jaws that move, right where my finger is right there, those are dead parallel and flat to each other at 0. So if I open the jaw up, there's a gap here that's linear as well. So I can use that now to measure length, like down the shoulder of this bottle. And then I get a reading there, 0.1014. And that's more reliable than using this end to measure the bottle, because this can tip around a lot, whereas with this one I get a square surface to bear up against. So it's a lot more repeatable. So those are the 4 major ways to use a caliper. When you're using it, you close the jaws and you wiggle the caliper and the object. Preferably they're both free floating in space, i.e. being held by your hands. And you make sure that it's all squared up and all the tolerances taken out, all the slop. But you don't push too hard, don't lean on it. You just want a firm closing action so that the digits stop moving around. And then you're at the action. You pull it apart and repeat the action with a similar amount of force. You get a new reading. Bearing in mind too that we're measuring along these jaws, which are ground flat and parallel to each other. And so when I grab something, right, I'm sort of assuming that the surface I'm grabbing is flat and parallel, and that I'm measuring for all of that surface, and I'm saying this is 0.9815 wide. But if I look in the jaw, I can see it's actually curved. So I'm not able to actually get in and measure that curved surface. It's concave curved, so the tips can't get in there. There are other instruments that solve those problems for you. But do bear in mind that you're all you're doing is putting 2 planes around something and measuring it. So you're measuring the maximum condition of it, not necessarily the subtlety of the force. Let's slip back to the slides here and go on to micrometers and pitch gauges and a few other gauges which we don't have in hand. So a little bit of these are the exact photo of the calipers we have in the center. Hopefully we'll get these replaced at some point, but this is relevant at this time. So this is outside, inside, depth, and then this drawing actually doesn't have that step in the back, the dial scale, how to lock and move it. Bear in mind that most calipers have an accuracy of 1/10,000th of an inch, and shouldn't be relied on for more than that. So this is reading the caliper here. So there's the 1 inch, which is the major digit, and then there's the sub-hundredths of an inch, which is in this case 3, and then 1 full revolution, which would be a step between these two digits here. You read off that final one, 7. So a micrometer is a much smaller measurement range. It can only go to 0 to 1, most of them. You can get micrometers up to larger sizes. I've seen 2 and 3 foot micrometers, but they're hanging up on walls and aren't used. They're just there to be impressive. Back in the day, they all presumably were able to achieve an accuracy of 1/10,000th of an inch over that large size, but they were fabulously expensive. And people don't throw them away because they're so beautiful and so expensive. But there's better tools now, coordinate measuring machines and various other modern digital tools that'll do those large spaces with better accuracy and confidence. And they're easier to handle. As it mentions here, micrometers are fragile, so you don't want to crank down on them or use them as a clamp or anything else like that. So it's a light and consistent touch. Usually there's a thimble ratchet in here that lets go at a certain pressure to help maintain this. Bear in mind that at 1/10,000th of an inch, we're starting to get to the point where thermal matters and discipline and measurement make important differences in the outcomes. Parts of a micrometer. So there's the ratchet stop and the thimble to turn it in, the anvil, which is stationary, the frame, the spindle. You can get these in non-spinning and spinning types, and a lock. You can use the lock to turn this into a go, no-go gauge, so that if the micrometer goes over the part gently with the same considerable amount of force, it's in the correct location. Okay. This is a micrometer with a vernier on it. These are a little tricky. We're going to have one more slide on how to use these. But basically, this final graduation is the last digit. And the closest line up with the vernier, you can see it better in this photo over here, is the last digit in the readout. And basically, this graduation is 11 units wide versus this graduation, which is 10 units wide. And they're perfectly aligned with each other, so that only one will match up, and that's the last significant digit reading. So we start with the first large number, 2. Then we add 25,000 steps here, so there's 2 of those. So it's 50 thousandths, and then we get this major barrel number here. So that's closest to the 4. And then we pick up the vernier here on the back. Couple of sample problems for reading these out here. Now these are more common than you think. They're not used often. So where they end up is on the large, unusual, occasionally used, but got to have it because it's the only way you can make that measurement instrument. And you don't want to buy a new modern digital version of that. The old one works just fine. So knowing how to use these is handy. My top recommendation would be to come into the center and to give this some practice. It does appear as a practice problem in the volunteering set. Thread pitch gauges will measure the pitch of threads in threads per inch or threads per millimeter. And they're how you can back out what arbitrary thread you've been handed or have found or have just manufactured is. There's instructions on how to use them that are readily available. I won't do a hands-on demo for this one, but just so that you're aware of them. We also have functional thread pitch gauges now in the center. They're hanging up in a column, and you just try and screw your bolt into there's one hole of each example and one bolt of each example. And you just try and screw them in and find out what it is. Telescoping gauges transfer ID measurement to OD measurement. And basically this top of this T-spring is spring loaded, and there's a little cone. You can see it in the photo. There's a little spherical section in there. And you put this inside a bore, let's say a cylinder bore of an engine, and you firm up the friction at this end so that as you rock this in the hole, it closes, but then doesn't reopen. And you go around and you find where it just barely rocks with a little bit of motion as it goes by, as you rock it back and forth, a little bit of resistance. Then you pull it out and you measure it with a caliper or a micrometer. So you can get a pretty accurate ID measurement to turn into an OD measurement that you can use with a more convenient tool. There are precision bore gauges. They're quite expensive. And in large sizes, 4, 5, 6-inch sizes, they're eye-wateringly expensive. But they will measure bores quite accurately to a 10,000th of an inch without having to do this intermediate step. A full set of these, though, is only $50. So it's fairly attractive. Gauge blocks are a little bit of magic. These are super precision blocks of length. They were originally called Joe blocks because they were a shortening of their inventor and manufacturer, Johansson, from Eskilstuna, Sweden, which is the Swedish capital of precision machining, sort of the founding location in the world of precision machining. But these are, you can send new gauge blocks or used gauge blocks you buy to the National Institute of Standards and Technology. Pay them $75 and they will tell you how long they are within 10 nanometers, which is a fabulously small distance. And these gauge blocks will reflect that faithfully for a long period of time. So you use these to verify the setup and the accuracy of other instruments in your shop. So these are sort of the master length standards of most machine shops. There are more sophisticated length standards in this, but they're quite expensive, and you'd probably only find them in optical metrology shops, places where they had to calibrate laser interferometers or other things like coordinate measuring machines. But a set of gauge blocks is super handy, and you can also use them to actually, I use them quite a lot to do machining and tooling setups where I need to set up one thing higher than another thing in a vise with a pretty good level of tolerance. I can use these to stack up a pretty precise height. A few other measuring tools that the center has that are useful. A height gauge, which goes up on a surface plate and functions like a caliper, but is a little more accurate and a little more flexible. So this can be moved around on the surface plate and can measure multiple setups in an object or multiple dimensions in an object in one time. Protractor measures angles fairly accurately. Feeler gauges, you can use these to slip in between things and find very small gap distances. And then this is a precision depth gauge. It's essentially a micrometer with a pin on the end of it and a very flat parallel ground surface. So use these to measure slots or grooves to get precise depths of those. When you're choosing a measuring tool, you should try and match the range, resolution, and then select the easiest thing that's there to use or most affordable thing. These are just considerations. You could buy a massive coordinate measuring machine that costs a couple $1,000,000 that can measure huge ranges, have high accuracies, great amount of flexibility, but there's a big expense in there, and it's not too easy to use at the beginning. It takes a while to set those things up and make sure they're calibrated. And you can measure things quite well with a ruler for most applications, particularly if you keep design control, and you can give yourself a lot of slack.